It's my pleasure to introduce our guest speaker this week, Tiffany Rivera, who's a good friend and colleague of mine down at Westminster College. Tiffany's education path brought her from Northern Virginia Community College to George Mason to Boise State, where she earned her master's degree. And then she went overseas and got a PhD in Denmark at, how do you say that, Roskilde University, working on an Earth-time project. And then came back to the U.S. to Boise State for a postdoc with Mark Schmitz, who many of you saw a few months ago now, 2 months ago, and here at BOS. Before becoming an associate professor at Westminster, we've had many hats, from National Park Service Park Ranger, professional geologist, Smithsonian docent, and I can speak from personal experience, master hip hop, mixer for long road trips on fieldwork. Great music taste.
Thanks.
Tiffany's a petrochronologist, so she combines the use of high precision geochronology and geochemistry and in situ measurements of those aspects of geoscience to ask a bunch of questions largely centered around igneous processes. So, long history of research in composition of caldera-forming eruptions, particularly in the Yellowstone system, right here in our own backyard. From her PhD studies, continues to work on questions about the geologic timescale. With our research programs. Tiffany can also teach us all a master class in mentoring undergraduates in research and getting those students empowered to present and communicate their science via professional society meetings as well as publications. She's mentored tons of students at Westminster, some of whom I've had the privilege to work with in my own lab and write papers with as well. And today she's going to share combine a lot of these highlights with her recent ongoing work in the Mineral Mountains. So take it away, Tiffany.
Thanks Pete, and thanks for having me back at DLS. I was here, I think, in 2015 when I first started at Westminster to talk about the work that I was doing out in Yellowstone. And so in the last 5 years, kind of bringing it home and looking at volcanism in Utah. And so this work, I'm not the first person to work on understanding the evolution of the rhyolites in the Mineral Mountains. Barb did a lot of this work back in the 1980s, 70s. It has actually stemmed from reading some of these legacy papers and legacy data out of the Mineral Mountains. So this is a view of one of the canyons that I'll talk about in the Mineral Mountains. And an idea, this is right next door is one of the rhyolite domes that we've been working on. And so the juxtaposition of these two very different types of rocks makes for some very stunning scenery out in the Mineral Mountains. I am getting, excuse me if I have a coughing or sneezing fit in the middle of this. Okay, so the Mineral Mountains located right off of the I-15 corridor. So we are, up here in Salt Lake. Just take I-15 down. This is the town of Fillmore. The cones that are being quarried right out here and the lava flows, and these are the Tabernacle Hill lava tubes, if you've ever been down there. So if you just continue south a little bit further, the Mineral Mountains are actually this range right here. Okay, so it's like the first range to the west of I-15, just about the town of Beaver. So. Oh, okay. Okay, so, I don't know. So when we zoom into the Mineral Mountains, okay, here is our topography, and you can see some of these little domes that are highlighted by the little triangles. There's another guy up here. And then just here on the right is the geologic map of the same area. I'm going to show this satellite image quite often today, and our reference point is this little kind of kidney shape the obsidian flows that we've been working on. And so you can, this guy is this guy here. In the south. You can also see this little establishment right there, which is the Utah Forge site. And so early work, this is a 1989 paper, identified ancient seismicity and current seismicity at the Roosevelt Hot Springs geothermal fields. And so this is our little kidney-shaped friend here, which is bound to the north by a fault, and then also on west. Okay. Oh. Man. I just have like a lot of energy or something sitting through this. And so this is the site of Utah's #1 geothermal project, which is the site that many people in this room and I am not involved in this in mountains. Instead, what got me involved in this area was actually from the geologic timescale. So the Pleistocene basalts down there, we thought had the potential to record the transition between the Matiuma and the Bruns geomagnetic polarity crons. And so my idea was, if we went down here, sampled some of these things, perhaps we could actually catch the reversal. Because if you're familiar with any of the current debate over the timing of this thing, it is hotly debated when this reversal actually took place. So I got involved in this project, actually thanks to Pete. Like when I asked him about it, he's like, oh, I have somebody else who is also interested in working in the Mineral Mountains. And so then it just became this giant project. So, so we are looking at rhyolites that kind of span the transition between the Matiama and the Bruns crons. And this is just a set of some dates and polarity from a 1978 paper of a number of those different units that are kidney-shaped obsidian flow, so from those two canyons. You'll notice that our precision on these things isn't all that great. And so if you are, and these are 1 sigma uncertainties. And so if you think about trying to resolve out the eruptive stratigraphy, you know, essentially these things all erupted at about the same time. So one of the goals that that I try to achieve is 1 per mil precision. So thinking about dating these things with such high precision that we can actually develop an eruptive stratigraphy for the entire range. Seriously, every time I touch it, it might be this, is it the static? Yeah. Okay, so our project goals, as I mentioned, is to improve the eruptive stratigraphy throughout this area. So thinking about the order of events that these things erupted and how much time the volcanic activity spanned within the range. We also wanted to look at the polarity of the units, confirm the polarity, see if we can capture that Matiama-Bruns transition, and then obtain new geochemical data and how that connects the eruption of these things to one another, and then also to the surrounding ground, and then come up with some sort of plumbing system for, I'm going to try to touch something else first, for the entire range. Christoph's laughing at me. Sorry. Okay. Okay, so these are sample sites. Again, I mentioned that we're going to see this map quite often, and so I've kind of grouped these into 3 different locations. And so they're color coordinated through here. This is where we sampled, and anything that you see in green over here are different types of granites. Okay, and so I'll talk about these a little bit later in the talk. They're you know, roughly Miocene in age. And they are now exposed in some cases at about like 9,000 feet, which is up here. Okay, so 3 different areas. Okay, sorry. So I've just called these non-canyon, right? Non-canyon flows, Wild Horse Canyon, which is this one here, and then Ranch Canyon in the south. So our 2 big hypotheses here. One is that the eruption ages of these rhyolites gets younger as you move up the canyons. Okay, and so that the youngest eruptions actually have occurred at the valley floor in the the oldest eruptions at the valley floor and the youngest ones at the higher elevations, and then that this is coupled with the geochemical evolution. So the more primitive lavas, the older lavas have erupted at the valley floor, and then more evolved younger lavas at higher elevations. So these are the two things that, that we are testing. Okay, our workflow includes argon geochronology. This is being done at the University of Wisconsin-Madison with my colleague Brian Jika. We are dating single sanidine crystals extracted from these rhyolites and doing primarily incremental heating on single sanidine crystals. And so I think to compare it to some of that like previous potassium data, you know, the level of material, the amount of material that we need has really been reduced since, you know, the 1970s, where we can do this on one single crystal. If we're not looking at the rhyolite domes and we're instead analyzing the obsidians, we're also doing incremental heating on small aliquots of the obsidian glass. And we're achieving precision levels far below what those potassium argon dates were doing. And so I'll show you some of those as well. Also working with Pete on obtaining some paleomagnetic data. And this is not from the Mineral Mountains, but great pictures showing a couple of my students who have since graduated working out in Yellowstone, using Pete's drill and Pete training them on how to interpret this data out in the field, or how to collect orientation data in the field. Okay. Our workflow obviously starts with field collection. We will go out to the outcrop. You can see a Homer bucket out here, and collect about 5 gallons worth of rock. We do this in order to also try to extract zircon from these, and so we obtain a big bulk sample of our rock, so that way we can process more in order to get a greater zircon split from this. We also do it in the events that somebody else might want to do other types of data collection on these, and so we have to share researchers. We obtain thin sections. We make thin sections in-house. We also get them done at Wagner Petrographic. And then from here, we will take these thin sections down to BYU and image some of our grains. So here's a nice quartz grain in thin section, and then also in CL, where you can see very nice zoning through there. And then we will obtain EMP analyses on our Feldspars, and I'll show you some data from that as well. And then finally, not finally, but simultaneously, our samples are being sent to the Wisconsin lab, where we're doing these single crystal analyses. So each one of these is a single sanidine crystal experiment that's been incrementally heated. Each sample is giving us a plateau age. So I'll show you a number of these, and instead of talking about I'll just lump them all together and instead talk about a weighted mean age. So this weighted mean age is of all 9 of those analyses. Coupled with that is the our paleomagnetic data here, and this example flow is showing a normal polarity. Okay, so I'm actually going to start with our non-canyon flows. This is the Bailey's Ridge obsidian, and then also what we call North Dome. This is the outcrop of the Bailey's Ridge obsidian, and this is Pete and Grant for scale. Okay, it is obsidian. There's nothing very exciting about it in thin section, but the obsidian actually gives us really nice age data. So this is the plateau diagram from that, just one single experiment from incremental heating, and it produces an eruption age about 50,000 years older than that previous potassium argon age. And so it's no longer just at that boundary of the Matiuma Bruns, but it actually pushes it back a little bit further into the Matsuyama Kron, and a very nice reverse polarity. If we head over to North Dome, this is a view looking away from North Dome rather than at it, but we can see that right next to us is some of that granite, and this looks to be like an older little cinder cone, and I-15 would be back in through here. Okay, so now we're at North Dome. Here we were able to image some of the Feldspars, and their compositions are plotted as A, B, and C. This grain up here is albite 81 or so, not a whole lot of zoning. It's not chemically zoned either. And then the grain down here is about AB 36, orthoclase 63. Again, from core to rim, so not chemically zoned. So from 2 feldspar thermometry, we're getting some sort of crystallization temperature around 740 degrees. Okay, plateau diagrams. The thing to note here is that everything is nice and homogeneous. So regardless of the grain that we chose to date, it's giving us very nice plateau ages, and they all form a weighted mean age of about 519 MA and returns a normal polarity. Okay, so this actually is great news because it coincides with what we would expect from our geomagnetic polarity timescale. Okay, I'm actually going to move to the southern canyon, Ranch Canyon, which is this guy down here. And this was the opening photograph showing the South Twin flat dome, which is this guy, and then the granite. And so that picture was taken right up this canyon, kind of looking back at this dome and this granite over here. Okay. This is Grant with Pete's head in the foreground. Grant drilling into this, you can see that the outcrop, it is a vitrified rhyolite. It's a nice big dome, real easy drilling, made for some great dating as well. It was quite a walk to get up to once we left the truck, and it was blazing hot out there. And so here, when we look at the feldspars, the chemistry seems to relatively be the same, right? So if we're comparing it to North Dome, the molar proportions of our 3 end members are relatively the same as what we found with North Dome, although we can pick up some different textures, and then also with this guy up here, you can also start seeing some more zoning. Okay, so not too different from what we saw in the north. Our age on this, right, again, not too different from what we saw in the north, but we are improving that precision, getting down to that 1 per mil level. Okay. One of my favorite outcrops ever is this guy. It is the Ranch Canyon Pumice Quarry. It is relatively easy to get to. It is an old pumice quarry, and there's just like giant pumices laying all over the road. It's absolutely beautiful. Here are my colleagues for scale on this thing, and I'll show you a closer view of this, which looks like my student Hannah Peacock, who did most of the work for the Mineral Mountains project. And so again, zooming in, you can see these giant pumices. This is a class-supported deposit, very little matrix, and so I've interpreted this as being like a pyroclastic fall deposit. Okay, so we tried to analyze some of the pumice clast in there. The feldspars actually come back really nice, and I've highlighted 2 very different feldspars. This guy here is 100% orthoclase, and then it zones out to 100% anorthite. And so that's telling us something about magmatic process, likely that we are seeing some sort of mafic influx to drive that composition back up to its calcic end member. And this one here shows actually the opposite chemical zoning from this one over here. So I think they're giving us insights into what's happening within these individual magma chambers. Exactly what that is, I haven't fully came up with a an interpretation yet. But here you can see that we are spanning both kind of, or all three end numbers of composition. So we saw. What we weren't able to do was obtain any argon dates on these yet, but that is planned for the future. So now I'm going to walk you through Wild Horse Canyon from our the valley floor up towards what we call Bearskin Mountain at the highest elevation. Okay. In the middle, let me point out here, in the middle we have a series of 3 domes. These 3 domes, they're in thin section. They look very similar. Their geochemistry is very similar, which I will show you here in a few minutes. And so I've kind of lumped those together. And instead of analyzing all 3 of them in detail, we just 1 or 2. So this is an example from one of those domes. And you can see that the composition of the feldspars tend to be a little bit more anorthic relative to the ones that we were seeing at those higher elevations in the other locations. So here the chemistry of things tends to be a little bit more, and you know, we're making some really nice zoned feldspar, obvious disequilibrium textures. Okay, and here's another one, kind of working your way up the canyon, where again we can see that there's a spread in the composition of these feldspars. This one perplexed me because of this grain here. Okay. And if you remember back to your mineralogy classes, when you were learning optical mineralogy, you knew that anything that's kind of like hexagonal shaped and extinct in cross-polarized light would probably indicate that it's a garnet. And trying to explain away a garnet in one of these rhyolites had me on edge. And so turns out we analyzed it, and it's just our old friend quartz looking down the C-axis. Right, a petrologist, okay? But it has to be one of the coolest things you find when you're like, I teach about this, and then we actually like, you know, get one in thin section. Okay, so you know, we went, so that was this guy here and this guy here. Back to our map, we are now out at a location called the Wild Horse Canyon Flow, which is this guy here. The legacy data says that it has a reverse polarity, and based on the chemistry and the age of our Bailey's Ridge, it says that it should be about, you know, 0.8 MA. And so we wanted to go back out and resample that one. We got a new age on it, which didn't suggest that it was reverse polarity. So we went back out, we drilled this one, this Pete and Emily here out in the fields. And our data for this came back as a plateau of about 741 with reverse polarity. So it is an obsidian flow. Its chemistry is the same as Bailey's Ridge, but it is not the same flow. Okay, this is a different interpretation from previous workers, and it puts that Wild Horse Canyon flow as being erupted into the Bruns Kron, which likely means we captured at least an excursion, if not the actual transition between the Matsuyama and the Bruns. So we did find something cool in terms of polarity. But these are 2 entirely different flows, same composition. Okay. And then a summary of our geochronology out here. So the Wild Horse Canyon flow, 741. The Wild Horse domes, the 3 in the middle, about 767. And then 588 and 539 at the highest elevation. Okay. So this is a summary of everything that we have collected so far. You can see we didn't capture that transition, but we've been making pretty steady progress on figuring out all of the eruption ages of the rhyolites across the range of the Mineral Mountains. We still have a couple left to do, but for the most part, this is what our new stratigraphy looks like. Okay. Okay, so going back to those 2 hypotheses. Hypothesis 1, right, are things getting younger towards the higher elevation? Okay, and when we add our ages on, it looks like this. Okay. in general, it does appear to get younger as we move up into the higher elevations, with the exception of this guy here, which is our Wild Horse Canyon flow. And we think that that was sourced out of one of these three domes and has since flowed down the canyon. Our next question is, does this age progression get reflected within the chemistry? Okay, so our hypothesis is that our more primitive lavas are near the canyon floor. And so this is what our chemistry looks like. Okay, I just want to point out our scale here. These are high silica rhyolites, greater than 70% silica. Okay. And so, and this is a very expanded scale, so we're only spanning 2% silica here, which isn't a whole lot in terms of rhyolite. If I was to put this on a TAS diagram, okay, so it looks like there might be some kind of break between the Ranch Canyon and the Wild Horse Canyon. There does appear to be a slightly different trend between the two canyons in terms of barium strontium and rubidium strontium. But overall, because they're such evolved rhyolites, their chemistry appears to be pretty much the same, okay, regardless of where they're in. This is a plot of niobium tantalum. Green Chemical Geology 1995, where he was trying to look at kind of a global signature for niobium tantalum and put on different types of granites. I've added to that some Yellowstone volcanic field basalts, Huckleberry Ridge Tuff, and then the other caldera forming eruptions on here. Our Mineral Mountain stuff trends this way, which could actually indicate that there's like a fractional crystallization trend across the range. Okay. And then we wanted to look at the rare earth elements of these different rhyolites, and then these are the patterns that we produce. And so if you remember back to your petrology class, as your europium anomaly increases, this signifies the fractionation of more plagioclase. Okay, so when I this in, I started looking at it by location, okay, by non-canyon, Wild Horse Canyon, Ranch Canyon. And then once I started looking at the data in a rare earth element diagram, I decided to regroup our samples patterns. And so I'm going to abandon this color scheme and instead do this one. So plotting anything that had a similar rare earth element pattern together, right, comes this way, and then how that corresponds to the location of our sampling. And now our chemistry seems to be a little bit more correlated with elevation. Okay, so these are our two rhyolites. These are our three central domes that you might remember had the distinct feldspar positions that were a bit more into anorthite than the others. And then at our highest elevations, these are the lavas that have the highest europium anomaly, the deepest europium anomaly. And so I set these up to just do a little bit of fractional crystallization models. This is very useful. I was quarantined over the weekend, and this is how I spent my time, doing fractional crystallization models. And so I started with our oldest lava, which is the Bailey's Ridge lava, which is one of the obsidians, erupted at the valley floor. And from that, I just overlaid a fractional crystallization model on top of it. And so it's going to drive liquid compositions up in this direction, actually away from the younger lavas, the chemistry of the younger lava. This is lanthanum versus samarium. Fractionation of feldspars and quartz is going to drive that away from the composition of the other lavas that we see. In order to get these compositions, I had to fractionate things like clinoprotein. In a high silica rhyolite, you're not going to be fractionating those minerals. Okay, so my kind of broad conclusion is that our three chemical groups that we have preserved within the mineral mountains aren't actually related by one single magma undergoing fractional crystallization. Okay, so that leads us to our next question about how granite influence these rocks. Okay, so we've got these high silica rhyolites that erupt at 9,000 feet through 17-million-year-old granites. And so there has to be some relationship or some influence between the granites and the rhyolites. And so what is that? And how does that help us resolve the plumbing system across the mountain range? So again, during quarantine, I put on a partial melt model of one of the granites. This is data from Coleman and Walker, 1992. The starting composition with this was a biotite hornblende granite. The reported data didn't even include all of our rare earth elements, and so this model interpolates a lot of the compositions between, especially some of the middle to heavy rare earth elements. So if I was to start with a biotite hornblende granite and melt between 1 and 20% of that granite, I would get this black pattern. Okay, if I was to start with that same granite, melt 1 to 20%, and then analyze the residue left behind, I would get this gray pattern. Okay, this is South Twin, the data for South Twin. And so I think this shows promise. I don't think it's perfect. And I think that by obtaining some new geochemical data on these granites that actually fill in some of our heavier rare earth elements, playing with this model a little bit more, that perhaps I could show that these rhyolites are partial melts of these granites. Okay. So in looking at the plumbing system across the range, I'm going to show you 3 different cross sections. The first one spans our non-canyon areas. These are totally hypothetical. I have no actual data to support that the plumbing system looks like this, but you know, best shot. So the geology looks like this. Towards the base of the canyon, we've got some Proterozoic schist quartzites, banded gneisses down here. That then in the middle of the canyon, you run into a site. The highest elevations, you have a quartz monzonite. Some heat source comes in, generates a melt that then can go rise up into these different granites, and then those can stall, fractionate, and continue to rise. Now with also looking at partial melting of these, right, we might not even stall out here. We might just heat these things up and come up to surface. And so perhaps this cyanite and this toid up here, they're different compositions are also contributing to the different compositions of the rhyolites we see at the surface. Okay. One interesting thing that I didn't point out on the maps was that these domes seem to have erupted where 2 different types of granites come together. And so I have drawn these to show that, yeah, the conduit for these things are coming up where the two granites are in contact. Okay. And then I will show you down here through Wild Horse Canyon, which shows all 3 chemical groups and the age progression from those central to the upper domes. And for that, I've come up with something like this. Again, I don't have any like true evidence that this is what it looks like, but we have some sort of heat source that comes down here at the base of the mountains. Melts off some of the cyanite to produce the chemistry that we see for the Wild Horse obsidian flow, the same cyanite that we see with the Bailey's Ridge flow as well to produce the same composition there. A biotite granodiorite here, partial melt of those to produce those central domes, and then a slightly younger, more evolved granite to produce the domes at the highest elevations. Now I'm going to kind of flip you around and show you a little cross section across the top of the range. Oh, sorry, I just added this in too. We are now starting to look at zircon data. Over winter break, I was able to go up to Boise State and extract zircon out of here and do some imaging. There are some textures in these things that definitely show that there are recycled grains. You can see this little guy in the center overgrown by nice oscillatory zoning. And so these morphological characteristics may indicate the recycling of some of those granitic zircon being picked up into the magma and then overgrown later by the rise. Something that I'm going to be exploring over the summer and into next fall. Okay, and so now I'm going to flip you around and give you a cross-section, hypothetical cross-section through the top of this range. And it looks something like this. We notice all of our eruption ages, right, could signify some 20,000 year recurrence interval, okay? But we've got some giant heat source down here that is allowing these little domes to form as we heat up the granite and partially melt this granite along the highest elevations within the mineral mountains. Okay, so in ultimate summary here, yeah, still to be determined. This is a work in progress. This is actually an unfunded project that I've just been doing kind of on the side. It's a lot of fun. It's beautiful scenery, and I think we're learning a lot about volcanism in central Utah and how these like small volume systems work in relationship to our like larger caldera forming systems. With that, I want to just say thanks to a number of people. Grant Ray Downing, who is here somewhere, came out in the field and was out in the heat and filling samples for us. Hannah Peacock, she is now a PhD candidate at UC Irvine, studying organic chemistry. She was a chemistry major at Westminster and worked with me on this project. She's the one who generated 99% of the data that I presented today. Stacy Henderson also helped us in the field. She will be defending her master's at Idaho State University next month. Stephen Kirby from the Utah Geological Survey, he was our field guide. McKenna Mickey Holliday, she's going to be off to grad school in the fall, and then Brian Jika, Pete Lippert, who are my partners in crime working on this project. So with that, I am happy to take questions about the Mineral Mountains or just open for discussion. So thank you.